lesson 12.8, congruent and similar solids. We've got two objectives, of course, identify congruent or similar solids, and then we're going to use the properties of similar solids as well. Stretch that out. Two solids are similar if they have the same shape and the ratios of the corresponding linear measures are equal. You guys know what similar figures are. And we can pick any measurement from one of the solids. Here if we choose the height and we choose the radius of the circles that make up the base and set those up as ratios, then we can prove that they're similar if they are proportional. And make this one larger too. If two solids are congruent, then they will have the following characteristics. Corresponding angles are congruent, corresponding edges are congruent, corresponding faces are congruent, and their volumes are equal. We're going to work particularly with volumes and surface area in this lesson, since we're talking about solids. Okay, here's our first example. We want to determine whether each pair of solids is similar, congruent, or neither. If they're similar, then we'll state the scale factor. We're going to do several examples of different shapes where we work through this type of problem. So the first thing we just need to do is take the linear measure. We can take the height of the small one and put it over the height of the large one, and see if it is equal to the base width of the small one over the base width of the large one. So 4 over 6 reduces to 2 over 3, and 8 over 12 reduces to 2 over 3. So since they are equal, then that means these are both similar. So what is the scale factor? It's 2 over 3. If they all reduce to the same thing, then the fraction that they reduce to is the scale factor. All right, let's try another one. Same question with these rectangular prisms, and we just have to choose how many measurements do we have to test to see if it's just 2 of them?
All 3, because sides are different.
We need to do all 3 of them to see if they all reduce to the same thing, because if we choose only 2 of them, what if this face is proportional or similar, but they have much different lengths? We have to choose them all. So we have to test all the measurements we see there. So we need to take 2.5 from the large one, and what does it correspond to on the small one? 1.5. And we need to take 3 from the large one. It corresponds to 1.7. And 6.2 corresponds to 3.4. All right, now these are weird numbers. What's a quick way that we can test to see if they are proportional? What does this line mean? Divide. What's 2.5 divided by 1.5?
Nope, they aren't. That equals 1.6 repeating.
This equals, this equals 1.6 repeating. And what's this one?
1.76.
1.76. We need to go any further?
Nope.
Nope. These are not similar, not similar shapes. Okay. Let's do the same exercise here with some cylinders. So we have to be careful that we're comparing the same dimension. So if I use 6.2 from this one, what am I going to use from the other one?
6.2.
Are you sure?
Yeah, sideways.
6.2 is what? But what specifically? What part of the base? Diameter. What's 6.2 here? Radius. Look at it. It goes all the way across. Okay. Don't let them trick you with the way they draw it. So it is 6.2 over 6.2.
Yes,
Okay, and then we would do 6.8 over 6.8. So are these congruent, similar, or neither?
congruent.
They're congruent. What's the scale factor of congruent solids? 1 to 1. Okay, the scale factor is 1 to 1. All right. Cones. All right, so if I choose 5 inches from the small one, what do I choose from the big one? 6. And then if I choose 12 from the small one, 14.4. Okay, got to make sure you set them up the same way. 5 divided by 6,
Yep.
0.83. 3 repeating. And 12 divided by 14.4, 0.83 with the 3 repeating. And so they are proportional, or they are similar. What's the scale factor?
0.83.
0.83 repeating, or how would we state it as a fraction?
8,300.
As a, well, no, because the 3 repeats. You can't change that to 100. As a fraction, it would just be this right here. That's the simplest fraction we can make it. So the scale factor is either 5/6 or 0.83 repeating. All right. Theorem 12.1, if two similar solids have a scale factor of A to B, then the surface areas have a ratio of A squared to B squared. We've already talked about areas of two-dimensional shapes before and how they work as this ratio is set up. We have to square the areas. And then the volumes have a ratio of A cubed to B cubed. So since we're working in 3 dimensions with volumes, we would have to use the cubed factors. So if the scale factor is 2 to 3, it's pretty simple to see that. For the area, square them, it's 4 over 9, and for the volume, cube it. So it would be 2 cubed over 3 cubed. And your calculators do that nicely for you if you don't know how. 2 times 2 times 2 is 8, and 3 times 3 times 3 is 27. So that's where they get that, right? So let's do a couple of examples. 2 similar cones have radii of 10 millimeters and 15 millimeters. What is the ratio of the surface area of the small cone to the surface area of the large cone? We can do this without even knowing the surface area of either one of the cones. We can still find the ratio just by using the linear measurements. So 10 over 15, and you don't have to, but you can. I think it makes it easier if you simplify. So 10 over 15 is 2 over 3. Then square it. Since we're talking about surface area, it needs to be squared. So the ratio of the surface areas would be 4 over 9. The next one, 2 similar prisms have surface areas of 98 centimeters squared and 18 centimeters squared. What is the ratio of the height of the large prism to the height of the small prism? You have to be careful on these where they tell you what order to put it in. So they want the large one first or on top, and the second one, or the small one second or on bottom. So the large one goes on top, 98 over 18. And we can simplify that first. Simplify it would be, anyone? 49 over 9. And then what do? What I have here is the ratio of the area, and I want to change it into the ratio of the height. Square root.
So 7 over 3.
It's going to be 7 over 3. It's the ratio of the height of the large one to the height of the small one. All right? The cylinders are similar. Find the height of the small cylinder. Okay? So we know we can set up a ratio of the volumes. So 270 over 640. Not yet. I've got to get these into numbers that I work with. Since these are volumes and I want to find a ratio that I can use with the heights, what do I have to do? Not the square root. We're not talking area, we're talking volume. How many dimensions does volume have? 3. So we want to take the cube root. But first thing we can do is simplify. Simplify, just drop the zeros and it's 27 over 64. Then we want to take the cube root of 27 over 64. So the cube root of 27 is calculators have a cube root button. Your scientific calculator should. They should have a way to do the cube root.
Where's the cube root?
Cube root of 27. We kind of just had this, but it's 3. Okay, what's the cube root of 64? 4. So the ratio of the linear measurement then should be 3 to 4. So now we can set up a proportion. So we'll do 3 over 4 equals, where does the h go, on top or bottom? It's got to go on top since it's the smaller one. H over 10. Now we can use the fish method. 10 times 3 divided by 4. Ten times 3 divided by 4. H is 7.5. So the height of this small cylinder is 7.5 inches. Okay? They give you the volume and you've got to find a linear measure. You've got to take a cube root. Regulation volleyball has a circumference of about 66 centimeters. The ratio of the surface area of that ball to the surface area of a child's ball is approximately 1.6 to 1. What is the circumference of the child's ball? All right, so we have circumference of the large one is 66. We don't know the circumference of the small one. That's what we're trying to figure out. But the surface area, the ratio is 1.6 to 1. So if we have the surface area, what do we have to do with that? We already have the ratio of the surface area. Here, we had the ratio of the volume, so what did we have to do? Cube root. Here we have the ratio of the surface area. Nope. Surface area has how many dimensions? 2 dimensions. So we're either going to square it or we're going to square root it. We already have the ratio of the surface area. We're going to square root it because we want to change it into the ratio for the linear measurements. So square root 1.6 1.26, and square root of 1 is just 1, so that measurement doesn't change. Now we can use that 1.26 over 1 equals 66 over, we're looking for the circumference of the other one, so 66 times 1 divided by 1.26. $52.4 centimeters would be the circumference of the child's ball. If they give you the ratio of the area and you want to turn it into the ratio for the linear measure, you've got to square root it. If you've got the ratio for the linear measurement and you want to find the ratio for the area, you've got to square it. All right? I don't know how else to say it other than that. Here's your assignment for today. It's like 15 problems.